Hello again, it's Mr. Stone here. So welcome back to grade 11 University Level Physics. We're still in Unit 1. This is Lesson 3. We're going to talk about motion from a graphical point of view. We're going to look at some motion graphs, some DT, VT, and AT graphs, trying to visualize what motion looks like, what uniform motion looks like, non-uniform motion looks like, and so on and so forth in terms of slope and area and other things. So should be some review from grade 9 in math class when you talked about these things in there. But we're going to do it a little bit more in depth and hopefully give us a sense of what graphs look like when things are moving. Okay, so let's get into it. So here I have a velocity time graph at the top here. I'm just going to make this bigger. Give me a second. I have a velocity time graph at the top. All right, so it's showing me that in the first, what's that? 8 seconds, the velocity starts off at 4 meters a second, but then slows down, and then at the 4-second point, whatever's moving stops moving entirely, but then starts going in the opposite direction. So this is now negative velocity. So let's say this is forwards. We can define that. Why not? Let's say this is forwards and this is backwards. Okay, so they're traveling away from you 4 meters every second. They're gaining 4 meters. That's what that would mean. Then they're slowing down until they stop moving. And then they start moving back towards you. They start speeding up. They're accelerating. This is representing this acceleration in the negative direction. That's interesting. So this curved line is actually representing quite a complex motion. Sorry, the straight line here looks quite straightforward, but it's actually representing quite a complex motion. But let's just worry about acceleration for now. Acceleration, we haven't really talked about it too much, but acceleration represents the rate of change of velocity. Okay, it's how much the velocity changes. So if I know that the velocity is the rate of change of velocity, how fast the speed is changing is called the acceleration. And in this case, it just represents the slope of my graph here. So rates of change, remember from grade 9, the rate of change of a graph could be determined by its slope. So if I want the rate of change of velocity, all I have to do is calculate the slope here. So I have a line. This is pretty straightforward. It's going from 4. What's the change in the y here is 8 negative, right? And then over 8 seconds, right? We're losing 8 meters per second in 8 seconds. 8 divided by 8 is 1. Negative. So we can go over here, look at 8 seconds, and we're going to put a dot here. Oops. I'm going to put a dot there for negative 1 meter per second squared. So this line, I can draw a line here, whoop, across here, to represent that the object here has a constant acceleration of negative 1 meter per second squared. That's telling me every second the object is losing 1 meter per second. So it starts out at 4, then after 1 second it's 3, then after another second it's 2, 1, 0, negative 1, negative 2, negative 3, negative 4. So it's losing a meter per second per second. That's another way you can actually, meters per second is the same thing as meters per second squared. Okay, then after 8 seconds, it's flat here. That's telling me that for these 4 seconds, the velocity is a constant negative 4 meters per second. So there's no acceleration there. It's staying the same speed. So I can then put a little interval here of 0 change. Did I go too far? I went too far, didn't I? It's still 12, not 13. Let me erase that dot there. Okay. So, and then it's abrupt here, so we're going to connect the dots with a line. Okay. When you do this, please use ruler. I can't put a ruler on my screen here. It'll mess up everything, but please do this with a ruler. All right, what about the next one here? We have 4 seconds. We're going from, what's this? This is from 12 to 16, and it's gone from -4 to 0. So that means we've gained 4 meters per second over 4 seconds. So that means that we have so 4 divided by 4, right? Slope is rise over run. So that's going to be 1 meter per second. So again, we're increasing our speed by 1. Oh, that is hideous. Wow. Let's try that again. A little bit better, not much. All right, and again, it's flat, so that's easy. That's the 0, right? Whoop. Across there and there. All right, so again here, we've gained 4 over 4. I can go through this a bit faster. And then again, it's flat, so there's no slope there. So that's the velocity, the acceleration time graph. We can call this an AT graph of this VT graph. All right. So you can see here we have a. Hi again, I'm back. We can see we have a VT graph. So this is saying it's slowing down while this slope is negative, right? We're going down the hill. The values of the slope are negative. Here it's flat, so there's no slope. So this is really telling us, going from the VT to HE, we're talking about graphing the slopes. So anytime we go from one graph to a rate of change of that graph, we just have to look at the slopes, right? So again, here we have, these are positive, these stretches are positive, right? So these have to have positive values. They're in the positive part of the graph. This part is negative, so it's in the negative part, and these 3 sections have no slope, so they are 0 valued. That's pretty straightforward, right? We know how to calculate slopes. You get some slopes, you put, and they're in the intervals. Now, this isn't physical, right? It's impossible to do this. We can't go from traveling, we can't go from having these jumps. You can't actually do that. They would be curved. This is non-physical, but let's not worry about that. We're just this cusp here. That's a bit strange. We can't actually do that from a physical point of view, but don't worry about it. We're just using this as an example. Now, this is the tricky part. What if we want to go backwards? And what I mean by that is, what if I want to go from a velocity time graph? So this is the same velocity time graph, right? To go from the velocity to its rate of change, I took the slope. But what if I wanted to figure out the displacements, how far it has gone over that same time interval in those 30 seconds? How would I calculate this? Now, this is an interesting idea, right? So let's say I'm traveling, let's use a little thought experiment. Let's say I'm traveling 2 meters a second, and I travel it for 10 seconds. How far did I go? That's pretty straightforward, right? If I travel every second, right, saying 2 meters per second means that every second I gain 2 meters. So if I do that 10 times, 2, 4, 8, that's going to be 20, 2, 4, 8, 2, 4, 6, 8, 10. If I do that 10 times, I'm going to end up with a new position of 20 meters. And how did I get that from 2 and 10? I multiplied. And that's like sort of an area of a box, right? If I had it on a graph, right, if my velocity was 2 and it was 10, I would end up with a box, an area in there of 20 meters, right? Because that would be meters per second. It even works out with units, right? 10 seconds. So that's meters per second multiplied by seconds. Seconds cancel out. We're left with meters. All right. So for us to go from a velocity to a displacement in the other direction, we have to find the area in between our graph and our x-axis. So we're looking for all these areas. These are going to represent our displacements. You can even break this up into a different section there. Okay? And we're going to break this up here as well, because it's hard to find the area of a trapezoid. Let's break it up into little triangles. All right, so first one here. So I know that I have, it's 4 meters per second over here, 0 meters per second over here. So in those 4 seconds, how far did I travel? And now, what's the area of a triangle? Do you guys remember the formula for the area of a triangle? Can you tell me? I'm listening through the interwebs. No? I can't hear you. I'm sorry. I wish I was in class. You can answer my questions. Oh well. So it's going to be 4 times 4, right? This is 4 over here. That's base times height divided by 2. So 4 times 4 is 16 divided by 2 is 8. So in those first 4 seconds, let's say assume we're going to start at 0. Now that doesn't matter, right? Where I start is arbitrary. Because this graph shows me the slopes. If I take my whole graph and shift it up or down, it's not going to change my slopes. In this example, we're going to start at 0. In all of our examples, I want you to start at 0 just to make things simple. Okay, we're going to start at 0. So 8. So that means in 4 seconds, I'm now at up here. This is 25. So each of these ticks are 5s. So it's going to be 5, 10. So that's going to be 7.5. I'm about here. Now this is the tricky part. So I started off with a velocity of 4, a positive velocity. So the slope of my line has to start off positive. At 4 seconds, my slope is 0. So that's telling me that my slope at 4 seconds is 0. I'm going to add a little tick here. Show that it's like a horizontal line. And it's this one. It has to be a positive value of 4 meters per second. How do I connect those? It's going to be a straight line. No, it has to be a curve. So it has to start off as a curve with a large positive, and then ends up, I missed. I totally missed. This is difficult on a touch screen. That's okay. Not really. Let's try that again. So we're going to start off with a positive velocity, and we end up with 0 velocity up there. Okay, so you can imagine there's a line here, like a flat line like this, that represents this, what we call a tangent to the curve. So that represents our 4 to begin with. And here, the tangent on this would be flat. So that would represent our flat part. Oh, eraser, please. There we go. So that's our first section. Starts off with a positive slope, ends up with 0 slope. The next one, now we're looking at the area between this purple line and this here, and notice it's below. Let's go full screen here so you can see better. Notice that it's below the axis. So this is in the negative region. I'm losing position when I'm in these parts. So this would be the same as this guy. So 4 times 4 divided by 2. So that's going to be negative. Let's get rid of these lines here. It's going to be negative 8 meters. Now, do I go over to the graph and go to negative 8? No, these are displacements. Remember, each of these guys are displacements. These are changes in position. Delta D. All right? So I was at 8, and now I'm going to lose 8, so now I'm back at 0. Okay, so notice all these things, these are changes in position. So I'm always starting from where I finished off in my first section. I finished off at 8, so then I have to then subtract 8 from my original point of positive 8. Positive 8, take away 8, 0. And again, here I have starting off with 0 slope. So let's add a little tick, a 0 slope tick there. And then this guy's going to have to be a negative slope going downwards. So it's going to have to be like that. And to connect those, I'm going to have to curve downwards. These should be symmetric. I did my best. Those should be symmetric, and they should have a curve like that. Next, so this is it makes sense, right? Because we said that we have a positive. We're going away at 4 meters a second. After 4 seconds, I'm going to stop. And this horizontal portion at 4 seconds means stopping. And then I'm walking back the same direction. So I'm speeding up. I'm starting from 0 meters per second to negative 4 meters per second. So I'm speeding up in the negative direction. So these slopes have to become more and more negative as I head down. I'm getting more, I'm positive, I'm getting more and more, I'm closer and closer to 0, and then I'm getting more and more negative. Okay, that's a bit tricky, but think about that for a bit. Next one, this is going to be 4 times 4, so this is just negative 16. So this is telling me between 8 and 12 seconds, I'm going to lose another 16 meters. So I was at 0 at 8 seconds, but now at 12 seconds, I'm going to have to be at, this was 15 about there, so I'm just below. Now, what's interesting here, though, is that the VT graph was straight, horizontal, sorry. So that means the velocity wasn't changing. So that means this slope cannot be changing. Do you remember what it means when a slope isn't changing? It means that it is going to be horizontal. Okay? So there has to be a horizontal line there at 16 meters. Is that 16? That's 16, right? That's 12? Yeah. Okay, that was negative 16. Sorry. So then we're going to gain another 8, except, well, negative 8. So we're going to get even more negative. So negative 16 minus 8, that's negative 24. So we're going to finally end up at 16 seconds over here at negative 24. And again, we're going to do the nice little curve because we're getting closer and closer to 0. This is very difficult on a touchscreen. Let's try this again. And now looking at this, I see this looks really, really bad. These curves should not do things like this. They should be smooth. When you do these problems, try to make them as smooth as possible. Ah, my goodness. I wish I had a chalkboard. All right, there we go. And then the same side, we're going to try to make it symmetric. All right, that looks better now. Okay, I didn't like how the slopes didn't match up. Now the slopes match up and it looks much, much prettier. All right, last bit here, 0. Not last bit, but between 16 and 20, the speed is 0. They're not moving. So, oops, at 20, oh my goodness, at 20, it's still going to be at 24. So it's going to go just across at 24. There's no change. Between 16 and 20 meters, there's no change in position. There's no displacement. Next one, again, this is going to be just like over here. So it's going to be 8. 4 times 4 divided by 2. So let's get rid of those lines. Confusing things. And we're going to add 8 to negative 24, which is going to be positive 16, which is going to be about here, right? Which is the same as before. So we're going to have a nice curve symmetric to our fourth bit there. Okay, and then the last part, in the last 6 seconds, we gain 6 times 4. So we're going to gain 24 meters. Remember, these are gaining or losing, right? So we're adding to our 16 point. We're going to add 24, so that's going to get us back up to 8 meters. Okay, so that's going to be, or sorry, we back up to 16. I apologize. I misspoke. So 16 was going to be about here-ish. Okay, and we can draw a straight line, right? Oopsies. Let's try that again. A straight line up to 16, right? Because this has 0 slope. So the it says, yeah, this VT graph has 0 slope. The speed at 24 seconds is 4 meters a second, and the speed at 30 seconds is 4 meters a second. So the slope of my line in my DT graph can't be changing. It has to be constant. So the slope has to be constant. Whenever we have a flat section in a VT graph, right? So this is flat here. This is flat here. The associated dt graph has to have straight sections. When my vt graph has diagonals on it, I have to have curves in my dt graph. Okay? That's this would be, so does it make sense? Let's go over it. Let's just see if we're right. We can always do that. We can always check. Okay, so to begin with, let's start at 0. We have a positive slope. Do we have a positive slope over here in our vt graph? Yes, it's 4 meters a second, so it's positive. So it's showing me here that I'm slowing down. I'm slowing down all along from 0 to 4 seconds until I stop at 4 seconds. Because this is horizontal, the tangent of the curve here would be horizontal. That means that the speed would be 0 at 4 seconds. Let's go down here. The speed at the velocity, sorry. If I say speed, I mean velocity. I apologize. The velocity here at 4 seconds is 0. So we're right on our first 4 seconds. Nice. All right, so now what are we going to do next? We're going to go from 0. We're going to start getting more negative and more negative. We're going to get it faster, but in the negative direction until we get to 8 seconds. Does that make sense? That what we did here? Okay, we started at 0 speed, and then we're getting more and more negative, 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 until we stop changing our speed at 8 seconds. Then we have a straight stretch here. So the slope of my dt graph is staying constant. The slope of this curve here is constant. And you can see that our rate of change, so the rate of change here is constant. The rate of change is represented by the velocity. So it's constant at negative 4 meters a second. And then the next section we're starting off at a large negative speed, right? The slope is negative, but we're flattening off. We're getting slower and slower and slower until we stop. So here, does that make sense? We're getting slower and slower. Yeah, we're negative 4, negative 3, negative 2, negative 1, 0. We stopped at 16. And then we stopped moving for the whole 16 to 20. So the distance isn't changing. So we have a horizontal section in the displacement here. Also, again, speed and velocity, I might mix those up. Displacement and distance, I may mix those up. Okay. Really, in this case, it doesn't matter. This is one-dimensional. You can use those words interchangeably. But yeah, it makes sense. We have 0 velocity, right? We're staying still. So we're at 24, and we're still at 24. Nothing's changed here. Okay. Then we're getting faster. We're accelerating. We're going from 0. We're getting 1, 2, 3, 4. We're getting faster and faster. So our slopes have to get more and more positive. Our slopes here are getting more and more positive until we stop increasing our speed, and then we stay at a constant speed for 4 meters a second for 6 seconds. So that has to be constant slope, so straight line for that whole 6 seconds. So we got it right. It all makes sense. Okay, just be careful. I messed up, especially on this little tablet here. Try to get the curves. Try to make things look like a nice, smooth curve. Okay. So that's what I just to recap here quickly. If we're gonna go from, hello again. If we want to go from, let's say, a dt to a vt graph, the rate of change of position is velocity. So when we're going from a position to a velocity, we're going to look for slopes. Those are going to represent our rates of change. And also, if I wanted to go to an AT graph, the acceleration of a velocity time graph is going to be the slope of that VT graph. So when we're going towards rates of change, it's always slopes. But if we're going in the opposite direction, it's going to be areas under the graph. Okay? So hopefully that makes sense, and hopefully you can use this little picture to help you remember which way you have to go, okay, what you have to do. All right, so what I'd like you to do for homework is there's a 4-sheet worksheet that is examples of problems using these ideas, just like the one we did in the example. I just like you to calculate those slopes, calculate those areas, and it's the tricky ones are the ones where we're going in the area direction, because we're going to have curved lines, and we have to be careful of what it looks like before and what it looks like at the end. I love that little trick that we can do where you say, okay, this is positive, so this has to have a positive slope. This is 0, so that has to have a 0 slope. So you make those little tick marks. Here, I can do it again. So I'll erase this here. Erase that little tick mark again. So I know this is positive, so that's going up to the right. I know it's 0 at the end, so that's going to be horizontal. How am I going to connect those? How can I connect those smoothly? The only way I connect those smoothly is going... I messed it up again. This is so difficult. There. Okay? With a curved line that eventually, after 4 seconds, goes flat. Okay, so go through those 4 sheets. There are a bunch of graphs just like this, and good luck. Have fun with those. Any problems, just contact me through Teams or email. I hope you guys by this point we're really getting a hang of how this course is laid out. And best of luck. I'll talk to you later.